Hello, this is Math 1428 Alternative Delivery for the 27th of March 2020, and please have your pencil and paper nearby as you're going through this lecture, as well as feeling free and in fact encouraged to I also want to again talk about the battle that we're fighting. And I ran across this quote. I like it. There is magic in fighting battles beyond endurance. I'm going to encourage you to make some of your magic today. Stay the course. I think it is very possible for us to continue teaching and learning even amid our crisis. Grades can be earned and rendered, and your educational goals need not be deferred. Today's lecture covers Chapter 4.5, and we have two learning objectives. For a rational function, we learn how to find the domain and graph the function, identifying all of the different kinds of asymptotes, and we also solve some applied problems involving rational functions. Turns out this first objective is rather involved, and so please take your time with this video. You may end up watching it more than once. This is what these rational functions look like, and if you look at the graphs you say, oh wow, there's some complicated behavior there, and that's true. We will learn about all of these different behaviors. So what is a rational function? Well, it's a quotient of two polynomials. So the numerator is a polynomial and the denominator is a polynomial. And you cannot have the denominator equal to 0. And so the domain of f consists of all inputs x for which q of x does not equal to 0. That's important. Please remember that. And so here's some examples where we're supposed to find the domains. So we're going to write in interval notation the domains for the functions, and we're going to realize that the denominator can't be 0. So I'm going to ask you to pause, do these problems in return, and see how you did. Let's see how you did. For the first one, x can't be 0, so the answer is all real numbers skipping 0, and that's how you do it in interval language. This one is also x not equal 0, so it has the same domain. This one, when we factor the denominator, we find out x can't be minus 2 and x can't be 1, so we skip those, writing in interval notation, and this is what we should write. This one, when you factor it, you say, oh, x can't be 3, and so that means this is the way you would write this in interval notation. This one, when you factor the denominator, you get this, x can't be minus 1 and x can't be 2. This is how you write that in interval notation. And down here, you're writing, you realize that x can't be minus 1. This is how you write it in interval notation. We have names for this. In general, the line x equal a, that's where it's not defined, is called a vertical asymptote for the function if any of the following things are true. So x goes to infinity or minus infinity as you approach those values. And you can see that these are the behaviors that happen at x equal a whenever there's a vertical asymptote, one of these four. Now, to determine the vertical asymptotes of a rational function, you determine the zeros of the denominator that are not zeros of the numerator. So if they have no common zeros, it's just the zeros of the denominator. So for determine a vertical asymptote for a rational function, f of x equal p of x over q of x, and those are functions that have no common factors other than constants. We'll talk about that later. So if a is a 0 of the denominator, then the line x equal a is a vertical asymptote for the graph of the function. So let's here then determine the vertical asymptotes for problem number 15. So pause and then compare notes with the answer. So pause now. Let's see how you did. Okay, so x equal 2 is the vertical asymptote. Let's do a similar thing for problem 9. This is a more difficult factoring problem. Let's pause and do the problem. Pause now. Let's see how you did. So when we factor the denominator, we get this. That means that this is going to give you the denominator, the vertical asymptote of x equal 3/2, and this one is going to give you the vertical asymptote of x equal -1. We don't just have vertical asymptotes, we can have horizontal asymptotes. That is where it levels off flat somewhere, like here it is y equal b, y equal b, y equal b, and y equal b. So you see you can level off to these asymptotes, and the asymptote is y equal b. So those are the ways, and these happen as you go to plus or minus infinity. So these are horizontal asymptotes because the line y equal b is horizontal. So let's determine the horizontal asymptotes of number 21. Everybody look at it, pause, and we'll think about it and see what happens. Let's see how you do. So the numerator and denominator have the same degree, and so if I take the ratio, I get 3/4. That's the ratio of the leading coefficients. So y equal 3/4 is the horizontal asymptote. This is true in general. If they have the same degree, the ratio of the leading coefficients is in fact the horizontal asymptote. Let's try number 23 here. Press pause now and do the problem. Well, the degree of the numerator is less than the degree of the denominator, so as this gets very, very large, y equals 0 is the horizontal asymptote. And this summarizes some of the rules that we talked about already. When the degree of the numerator and degree of the denominator of a rational function are the same degree, the ratio the line y equal a over b is the horizontal asymptote, where a and b are the leading coefficients of the numerator and the denominator respectively. When the degree of the numerator of a rational function is less than the degree of the denominator, the y-axis, or the x-axis, or y equals 0, is the horizontal asymptote. When the degree of the numerator of a rational function is greater than the degree of the denominator, there is no horizontal asymptote. Now, we do call this, though, something that is called a oblique asymptote, and we will solve those, and we'll solve those by first doing polynomial long division, which we learned earlier. Now, here's a drawing that has directions much like I often could ask. You make a hand-drawn graph of this, label all asymptotes, find the domain, the x-intercepts, and the y-intercepts. And it says check your work using a graphing calculator. We're going to have several examples that use these directions. I won't read them again, but let's try number 41. Press pause now. Let's see how you did. Okay, so here's the graph of the function. The numerator and denominator have the same degree, so the line x equals 0, or the y-axis, is the vertical asymptote. Thus, y equal 2 is the horizontal asymptote. If you look at the ratio of the leading coefficients, they're of the same degree. There is no oblique asymptote because those degrees were the same. The 0 of the numerator, which is the 0 of the function, is going to happen at -1, 0. So you see that's when it hits the x-axis. Since 0 is not in the domain of function, there is no y-intercept. And we pick some other functional values, but then we get a picture that looks like this. Now, sometimes a line is neither a horizontal nor a vertical asymptote, but it's an asymptote because the function gets closer and closer to that. This is called an oblique asymptote or slant asymptote. And in fact, in our book, it's always when the degree of the numerator is 1 more than the degree of the denominator. So let's do one and see what happens. So we have this, and we're going to do same directions. Okay, so we factor numerator and denominator. Pause, see how you do. Let's see how you did. Okay, you factor the top and the bottom, and that tells you that you have zeros at +3 and -3. So we can plot those. That's where we hit the x-axis. We also have a vertical asymptote at x equal -1. When we do long division, we find that x squared minus 9 over x plus 1 is equal to x minus 1. That means that is the oblique asymptote. But as x gets large, this term goes to 0, so that is the oblique asymptote. So as the line x equal minus 1, you can see that in my graph I show it as a dotted line, but I get closer and closer to that line as I go through. And here's the asymptote at x equal 1. You see it's going to minus infinity there, and it's going to plus infinity over here. Okay. Whenever I already talked about the zeros. Whenever we put 0 in for y, we get minus 9, so that's the y-intercept. It hits down here. You can't see it on the graph. And then you pick some other values. This is the graph that you will graph for that problem. Okay, this summarizes what we've learned about asymptotes. And vertical asymptotes occur at any value that makes the denominator equal to 0. The x-axis is the horizontal asymptote when the degree of the numerator is less than the degree of the denominator. A horizontal asymptote other than the x-axis occurs when the numerator and denominator have the same degree, and we have an oblique asymptote occurring when the degree of the numerator is one more than the degree of the denominator. There can only be one horizontal asymptote or one oblique asymptote, but never both. Actually, that's a little bit not true. There actually could, in some functions, be two horizontal asymptotes, but apparently we're not going to have examples like that. And an asymptote is not part of the graph of the function. You graph that as a vertical line. The following statements are also true. The graph of a rational function never crosses a vertical asymptote, but the graph of a function might cross a horizontal asymptote, but does not necessarily do that. So remember, graphs can cross horizontal asymptotes or oblique asymptotes, but they never cross vertical asymptotes. Some more examples, same direction. Here you're going to factor the denominator to look at the numerator, but you're graphing the entire function. Press pause. Let's see how you do. We should have found that the lines x equal minus 1 and x equal 3 are vertical asymptotes. Y equals 0 is the horizontal asymptote. There is no oblique asymptote. 1 is the 0 of the numerator, so that is the x-intercept. We hit there. And when we put 0 in for x, we get 1/3, so that means 0, 1/3 is the y-intercept. And you can pick some other points, but this is the graph we should have, and you see our vertical asymptotes and our horizontal asymptotes and our zeros where it hits the axis. Same directions for number 77. We're going to graph this. Please hit pause, do the problem, and come back and we'll compare notes. Let's see how you did. This is the factorization, and so we find that the lines x equal minus 1 coming from this one and x equal 2 are the vertical asymptotes. Since we have the same degree, y equal 1 is the horizontal asymptote because it was 1 divided by 1. And you can see that y equal 1 is the horizontal asymptote. There is no oblique asymptote. To make the numerator 0, you take x to be 0, so 0, 0 is the intercept. From part 3, we also see that 0, 0 is the y-intercept. So we pick some other function
Number 49.
values. Now what happens here, though, is you see we get a rather complicated expression.
Hit pause.
And also note that on this
we'll
one,
see how you did.
Let's see how you do. Pointer. So when we factor it, you should have factored it this way. Now that means that there are vertical asymptotes at x equal minus 1, but at the point where x equal minus 3, you see that that's a 0 of the numerator and denominator. That means there's a hole when x is equal to minus 3. When x is equal to minus 3, the function is getting closer and closer to the values of 2. So this is minus 3 comma 2. That is called a hole. It's not in the domain, it's just a hole in the function. The numerator and denominator have the same degree, so y equal 1 is the horizontal asymptote. The only 0 of the numerator that is in the domain of the function, minus 3 is not in the domain of the function, is 1 for x, and so it's a 1, 0 is the root. That's where you hit the x-axis. When you take x to be 0, you will get y is minus 1, and so 0 minus 1 is the y-intercept. You pick some other values, but this is the picture you get, and please note the hole. That was the biggest feature of this problem. Number 67, please read the problem, factor the numerator and denominator, and proceed. Press pause. Now, let's see how you did. Alright, so when we factor the numerator and denominator, we get this. Again, we see we have a hole at x equal minus 4 because that's a common factor. And so that means that the only vertical asymptote is at x equal 2. So x equal 2 is going to be this vertical asymptote. And we'll have a hole at this point, which is minus 4 comma 4 over, or minus 4 comma 13 over 6. Since the numerator and denominator have the same degree, the asymptote is 3. It is y equal 3 is a horizontal asymptote. The only other 0 is the one we get from the numerator, and that is 3x minus 1 is equal to 0, so 1/3 comma 0. When we substitute 0 into the function, we find that we get 1/2. So the y-intercept is 0, 1/2. You pick some other functions, other function values, I guess, but this will be the graph of the function. There are word problems, and here's an example. And I'm going to have you read it, but we're to find out the horizontal asymptote and say, what does it mean? Now, here we're going to say, this is asking the question, so what does n tend to as t tends to infinity? This is the dosage that we have, and this is the medical dosage. It looks like for different people of different ages, so the older they get, they still get medicine, but not as much, and so how does that change? And explain the meaning. Hit pause, and we'll go from there. Okay, so the asymptote is 0.16. That means that no matter how old you are, you're going to get a dose of at least 0.16 as t goes to infinity. The medication never disappears from the body. A trace amount remains. And we have, I guess, one more example. This is a matching thing, and this is kind of a review from the beginning of time, but it does include the functions that we have. I'm going to ask you to go through and do this matching problem, pause the video, and return in a bit. So let's pause now. Let's see how you did. Here are the answers. So now, more than ever, time is precious. Each day must count. Do the math. It will make you strong. See you after spring break. Take care.